Hi, I'm Zac Manchester. I'm an assistant professor in the Robotics Institute, and I'm the PI of the Robotic Exploration Lab. And we work on, in my lab, something called motion planning and control. And I like to think of this as the science of moving things. It's sort of how we get robots and other systems to do what we want with algorithms and software. So to give you a little bit of an idea of why we work on this stuff and what it's all about, I'd like to start out with one of my favorite robots, the Mars Curiosity rover. Curiosity's been on Mars for about 8.5 years in one of the harshest environments imaginable. And in that time, it's gone about 23 kilometers. This sounds kind of impressive until you divide those two numbers and see that that works out to about 7.5 meters per day. Why is this number so low, right? The answer is that Curiosity is not very autonomous. In fact, it's not really autonomous at all. There's humans driving it back on Earth. And so everything Curiosity does has to be analyzed, planned, and then commands sent up from the ground by controllers. And this leads to really high latency. And what my lab tries to do is make systems like this able to control their own motions and go where they need to go without human intervention. This is some work from my lab from a few years ago, showing planning on a dog-like robot called Little Dog. And you can see we can get these things to climb stairs, and the bottom right shows limping when it's had a damaged leg. So this looks really nice, right? It looks very animal-like, but the problem is that this stuff right now, these few seconds of motion you're seeing here, took more than 30 minutes to plan offline. So we're nowhere near being able to do this stuff online on the robot in real time like those mountain goats you saw. So what we've been working on in my lab for the last couple of years is trying to speed this up. So we've built new algorithms. We have a custom solver for this kind of stuff we call ALTRO. And we're right now about 1 to 2 orders of magnitude faster than kind of the standard off-the-shelf solvers that people use for this stuff on a bunch of benchmark problems. So this is great, but we're still an order of magnitude or more too slow for the dog robot or the mountain goat scenario that I showed you before. So we still have a lot of work to do. But this new solver technology has enabled a whole bunch of interesting applications in the meantime that I'll kind of tease a little bit. So we do a lot of work on space applications in my lab. And one area that's gotten really interesting recently is on-orbit servicing, so docking, proximity operations, trying to refuel satellites. So we do some work in that area. We also have a project with NASA to do trajectory planning and control for entry vehicles to land on Mars. And the challenge here is that you don't really know what's going on with the winds and you have a lot of uncertainty, but you still need to do a pinpoint landing and guarantee safety. So that's really challenging. We do some work in cooperative control. So in a multi-agent setting where you have multiple robots that need to collaborate and cooperate to achieve a common goal, we can build algorithms that let the robots talk to each other and coordinate their motions like this. We also similarly work on what's called game-theoretic planning. So this is a multi-agent setting where you're not cooperating, where it could be adversarial. And it turns out this is directly applicable to autonomous driving, to things like highway merging, where you have to reason about what the other agents are doing, but you're not directly collaborating with them, right? We also do a lot of work on small satellites. So this is what's called an attitude control problem. So pointing a small satellite, getting it to slew around and point cameras at the ground, say, or antennas at a ground station. And we've actually built 3 of these little satellites. One of my grad students actually built these in his kitchen over the last couple of months because of COVID restrictions. And these are going to fly next week, fingers crossed, on a SpaceX launch to demonstrate some of this stuff on orbit. The last thing I want to throw out there is that on the hardware side, on the space side in particular, we actually do a lot of open source hardware development and outreach stuff on these small satellites. All of the hardware for those satellites has been open sourced. The designs are publicly available, the code's publicly available. And we've had a lot of student groups at other universities actually build these things and use them in courses, and it gives you the ability to put together a satellite for a few $100s and puts it within reach for small student teams. So that's kind of a brief overview of what we're all about in my lab.